Sunday, Sunday, Sunday. Come on down tonight for the event of the decade right here in Dave's Garage and prepare to get annihilated as Bass Pro Shops and Walmart present the Mega Monster Language Racing Series featuring all of your favorite computer languages such as Rust, JavaScript, C++, and the amazing, the astounding, the unbelievable Python. One night only, one night only, one night only. Your free ticket will get you the whole seat, but you'll only need the edge as you witness more than 50 computer languages in a showdown so unhinged, we almost had to hold it in New Jersey. You better see it now while it's still legal, and it's all coming up right now in Dave's Garage.
Hey, I'm Dave. Welcome to my shop. Today in Dave's Garage, I'll be continuing the computer drag racing language series with two of today's top contenders, C# and Java. They're just a pair of the more than 60 programming languages that we'll be testing in this series to find out which produces the fastest code and where all the other languages rank relative to one another. You'll also get a guided tour of each of the languages and an introduction to its cool or unique features, style, and syntax, after which we'll be drag racing them all head-to-head using the same prime number algorithm, but adapted to that language. Believe it or not, we now have, as I said, more than 60 language versions thanks to volunteer programmers and a crack team managing all of the pull requests and the occasional bit of chaos and drama over at the GitHub repo. Don't forget to check the video description for a link to the real code. If you know another language that can be added to this giant matrix of languages, please do dive on in and contribute it. Same deal if you're an expert or even just adept at optimizing. You might wish to review the version in your favorite language to see if it can be perhaps made even faster. You've got time before the finale, even if the language has already been reviewed. Remember that all profits from this channel will be donated in 2021 to the UW Autism Center, so grab yourself a Dave's Garage mug from the channel store. Not only is it absolutely guaranteed to make your coffee taste better, but every sip will be imbued with the satisfaction of knowing you helped a kid with autism. I'm surprised anybody drinks coffee without one, frankly. Collect the whole set. Now, several viewers have asked that I put together a graphical leaderboard of some sort so that I can collect the scores in one place to review as we go. For example, we've already done PHP, Perl, Pascal, and so on, so we should collect those scores onto a list to start. Now, I used to be a fan of the TV series Top Gear, which reviews sports cars and such. They kept track of the relevant lap times on a simple magnetic whiteboard, and so if it's good enough for the BBC, it's good enough for me. But one aspect that always made it entertaining was that they would always use what they referred to as their tame racing driver called the Stig. They would introduce him alongside such odd claims as, some say his perspiration can be used to polish precious metals and so on. And now I will not do a British accent because I don't know how. Now, I can certainly muster a whiteboard and some markers, but what am I going to do for a tame race car driver? How can I pay homage to Top Gear in a suitable fashion? Now, I do have a white helmet and coveralls, but then I had a better idea. I'd bring in a ringer, somebody who looks like the Stig, but with tech credentials going back to the 90s like my own. And so to that end, I'd like you to meet Baby Stig. Now, Baby Stig might look familiar depending on your age and how long you've been doing this. Modeled after the Intel workers who wear what are known as bunny suits in the fabrication clean rooms, the dolls were actually part of an ad campaign that Intel ran in the late 90s. Baby Stig here stayed safely in his box for more than 20 years until I came along and rescued him from neglect. By the way, I'm pretty sure naming him Baby Stig would run afoul of the Top Gear lawyers, so we need a good name for the little dude. For that, I'm going to turn to you guys, the viewers. Please leave your comments on the video with your suggestion, and if somebody else suggests a name that you like, please upvote that comment. That way, I'll know which name suggestion is the audience favorite. I first saw these Intel characters when I was speaking at a conference around 1997. I think it was Networld Interop in Atlanta, but to open the show, a half-dozen Intel dancers in their bunny suits performed a tightly choreographed and very demanding dance routine. After a few minutes of this extreme exertion, the routine came to an end, and with all the dancers a-huffing and a-puffing, the lead dancer ripped off their head covering to reveal that it was actually Intel CEO Andy Grove, who was well into his 60s at that time. Clearly, they had rotated him in during the last seconds of the dance somehow, but it was done seamlessly enough that I didn't even notice. And so, after we've tested C# and Java, we'll enter their scores and the scores of the other languages already tested onto that new leaderboard. I thought a good place to start would be to enumerate the similarities between Java and C#. Now, the problem with doing that is that the languages are actually awfully similar. Both are statically typed, declarative languages that imitate the syntax of the C++ language to a great degree, while adding garbage collection and other conveniences that make life much easier for the programmer. Both compile to system-independent bytecodes. Those bytecodes can then be interpreted in the Java case or just-in-time compiled to platform-specific machine code once deployed in the case of C#. Now, if you've spent any time around Java, you've likely heard the term bytecode at some point. And if you're using C#, you've no doubt have heard of intermediate language, or IL. While not synonymous, they're pretty similar. They represent sort of instructions in an assembly language for a virtual machine sporting an imaginary processor. This idealized processor allows the code to be compiled to a generalized solution that is then later compiled, as I noted, to real machine code for the machine in question, or in the Java case, interpreted. That's why it's called an intermediate language. It's higher level than the raw machine language of the real machine itself, but more lower level and finer grained than the high level language it started its life as. Microsoft's intermediate language, formerly called MSIL but now called the CIL for Common Intermediate Language, is used by all the .NET languages. Whether you write a program in VB or C# or F#, it will be compiled to CIL along the way. One big difference with the CIL is that it's stack-based. Rather than using a ton of registers, it uses a stack. So whereas in, say, X86 assembly language, you might add 2 registers directly with the add instruction, in CIL you would first push the first variable, then push the second variable, then invoke the execute opcode. It would add the top 2 values it finds at the top of the stack, and then you would store the result. Unlike a normal assembly language that deals largely with immediate values and pointers, intermediate language is object-based. That means, for example, that there's actually a new instruction. It does what you'd expect, creating a new object of a particular type. That seems very high level for such a language, but object lifetime management is fundamental to the common language runtime languages. It also is for Java, and that's why Java's bytecodes are similarly object-oriented. In fact, tools have been written to translate back and forth between Java bytecodes and .NET intermediate language, which tells me they're reasonably similar under the covers. Now, there are some differences, such as enums being full types in Java bytecode, whereas they're largely treated as integers in intermediate language. I believe in terms of other differences, .NET supports value semantics, whereas everything has to be reference-based in Java. .NET natively supports unsigned types, which makes the instruction set a bit richer. Java includes the details of any exception specification right in the bytecodes, but .NET I don't think does. .NET expresses generics directly in its intermediate language, whereas Java only uses type erasure. And lastly, .NET supports the out and the reference parameters on function arguments, and so there are a few important differences. Bytecodes were intended to be used for interpreted Java, whereas CIL was always intended to be used for just-in-time compilation. My knowledge could be out of date here, but Java is never reduced to raw machine code, but rather the bytecodes are interpreted. That's not the same as interpreting the high-level language, and nor does it carry anywhere near the same performance penalty, but there might be some. If the fact that you can translate between bytecodes and IL leads you to believe that the languages are thus equivalent, that's not quite the case. We don't want to focus in too long on the IL versus bytecode issue because at the end of the day, that's merely the plumbing that makes possible the things we care about, the language itself and the execution speed of the programs that it produces. Intermediate language was designed from the beginning to support multiple source languages because Microsoft at a minimum had to deal with C#, Managed C++, and VB.NET. Java bytecodes only had to worry about Java, and so naturally, it reflects a closer tie to the language, which is probably a bit more restrictive. It might be a lot harder, for example, to write a functional language like F# or Scheme in bytecodes because that was never really one of the intended scenarios for it in the first place. That's only because of the Java focus, however. The language Lisp, which we will visit later in the series, also uses a bytecode stream. If I had to wickedly overgeneralize, I would say that Java bytecodes are more similar to BASIC's P codes, a set of tokens intended for quickly interpreting, whereas CIL most closely resembles assembly language intended to be turned directly into machine code. That sounds like something that could have significant performance implications, but that's why we're going to race them to find out. Before we do that, let's have a look at the actual source code. I'm going to start with the C#, in part because we've actually already seen it once before if you follow the channel. If not, you should definitely subscribe, turn on the bell, and check out the Python, C++, C# comparison episode.
Do it, Glenn! Do it! Do it!
The first C# we'll look at is my reference implementation from the original tree of languages in that episode. We're revisiting C# because A, I wanted to spend some time comparing it specifically to Java, and B, that original episode was filmed before we had all 60 languages up and competing, so there was no way to carry its score forward. Thus, we'll run it again today, but this time against Java. First, we'll take a look at what's known as Solution 2 in the Prime C# folder on GitHub. I wrote it not to be clever or even particularly fast, but rather to be exceedingly clear and easy to read. Now, whether I met that goal is up to you, but in a moment, we'll take a look at much more complex solutions that stretch the language much further. For now, let's start with my main function. The main loop runs until a total of 5 seconds has elapsed. We still keep track of the total time elapsed by recording the start time in tstart. Why not just assume 5 seconds? Well, imagine that each run took 4 seconds. The first would complete in under 5, and the second not until 8 seconds had elapsed. If you assumed 5, you would erroneously conclude 2.5 seconds per pass instead of 4. So that's why we always track the number of passes, total time, and then express the race results in passes per second, which is just the reciprocal of how long each pass took. As you can see, this implementation does the correct steps of constructing the sieve from scratch, running it, and counting it as a pass. The thing we don't know in a deterministic sense is when the sieve is actually destroyed. You'd think that when the pointer is reassigned that the original object can be deleted, but it isn't. It's simply marked as reclaimable. When the garbage collection begins, it should be easy pickings for the system, but it could stick around, including its enormous memory allocation for the sieve, until the system decides that it's time to clean it up. We don't know when that could happen, and therefore we don't know if any resulting performance impact would actually be included in our results. In C#, if you have a class that holds a particularly expensive resource, one option is to implement an interface known as iDisposable. That will enable the system to immediately reclaim those resources if your object is wrapped in a C# using clause. When a using clause goes out of scope, the disposable object contained within it is reclaimed immediately without waiting for the next garbage collection. Back in the day, I made the most use of that feature when doing database programming because, as you can imagine, you can't just keep a table lock or a big join or even a query alive forever until the garbage collector gets around to cleaning it up. You need to release those types of resources immediately, and the language indeed supports it. The run sieve function is the model of simplicity. While I'm biased because C# is admittedly my favorite language, I think that it's the most clear of any of these languages. It also likely helps that I wrote this one, so I know what I was trying to do and why. But I think if you have any familiarity with C syntax, it reads like an idealized pseudocode version of C itself, and that's part of what I love about C#. Next, we'll take a look at another of the C# solutions, a very complete one known as Solution 1. This one's by Kinematics, and he's put a lot of work into this one. The solution actually contains many different prime sieve solutions, some of which are faster than my original. That does come at the cost of some complexity. To run one of the sieves, you call the static run benchmark member of the benchmarker class. It, in turn, calls the run method of the appropriate benchmark runner. Assuming your sieve correctly implements the iSieve interface, it can then be called via its run and count primes methods. That framework may sound complicated at first, but it's pretty smart in that it allowed the author to write a lot of simple, small sieves and then swap them in and out in order to compare them to each other. For example, one sieve might use bits, the other's bools, and another might use bytes, and so on to track the sieve state. We can then compare those implementations where everything else is held constant and see the impact of just that single change. If we look at the sieve runner's run sieve method, we can see some of the interesting C# language features. First, the use of a function reference that can refer to any object that implements the iSieve interface. That reference is obtained by calling the getSievCreator with options that describe the type of sieve that you want to create. We ultimately hand that reference to the sieve creator off to the run multiple thread or run single thread function, as the case may be. Let's have a look at the var statement. What kind of madness is this? Well, you need to haze out a little and step back to see the forest for the trees on this one. It turns out that we're going to call one of two functions, either run multi-thread or run single thread. Which one we call is determined by whether or not the multi-threaded property is true on the run settings object or not. Whichever it calls, and here's the crazy part, it can return multiple things. In this case, it will return an iSieve reference and the number of passes that could be completed. Remember, in C, you can return a structure, and you could have multiple things in it, and in the C# case, you could just return a simple tuple of values. Imagine you had a function that returned employee name by employee ID. You passed the ID, and the function could return both the first and last names at the same time. One of the items being returned is an instance of the prime sieve itself, which allows us to call its validation and count members to get post-run statistics. I looked under the covers to see what was going on here, and it's returning the last instance of the sieve that was run. Now, that's more efficient than my approach of a dummy sieve used to collect stats and verify the results, but when you're running 1,000 passes a second anyway, sometimes simplicity is a fair trade-off for 1 millisecond. But for others, every millisecond is sacred, and I get that. To each their own, however, and I learned a number of things from this C# example. If you've not already seen it before, it shows how simple parallelization can be in C# as well. If we look at the implementation of run multithread, we can see that it runs thread count tasks in parallel, where each task is comprised of the work of creating a sieve and then running it. It determines how many threads to run by looking at the system's processor count variable. All that was needed to parallelize this workload was to simply change it to use parallel for, and the rest is done for us. You'll also see the use of the question equals operator. This has the effect of assigning the right hand to the left-hand side, but only if the left was null. If the left already had some non-null value when you hit this statement, then the right-hand side of the assignment is not even evaluated, let alone assigned. Jumping down to the print results function, we can see the use of two more innovative language features, select and aggregate. Select is a simple transformation, meaning it transforms something from one form into another. What's going to do here is to take each of the integer prime numbers that came back from get found primes and transform it into its string representation. So at this point, instead of a list of numbers, we have a list of strings that contain printable numbers. Aggregate is something of an accumulator. It's going to sweep up the list and put commas in between the numbers. Well, it might not be obvious at first, though. This is a one-liner mechanism for translating an integer list into a comma-delimited printable list. Once it has that list, it writes it to the console. And finally, we'll visit the runStructs function only briefly to observe the use of the stopwatch class. Stopwatch provides simple methods such as start and stop, and then you simply look at the elapsed time property, which will tell you how long the stopwatch was running. It avoids having you keep track of the last timestamp and doing the math yourself. Finally, pausing at the last of the three solutions, it turns out to use the unsafe keyword for some raw memory management techniques, which isn't something I want to emphasize here and now, so we'll pause only briefly enough to note its use of the aggressive optimization declaration on the runSiv function. C#, like all of the .NET languages, allows the source code to specify relevant information about and preferences for the function to the compiler. It's at that point that I'll leave the C# and we can turn our attention to the Java implementation. I think of the two solutions we have, the one listed as Solution 1 most closely follows the original template, so we'll start there. Now, in my humble estimation, Java looks even more like C++ than I thought the C# did, so it's slightly less friendly perhaps in that the time calculation in the main is done in milliseconds rather than fractional seconds, but that's a pretty minor thing. Beyond that, main looks very similar to what we saw in the C# version. I'm not a big fan of how the map is initialized, though. I looked at the more modern Java ways of doing it, but they involved collecting streams of string arrays, and they were certainly no more clear to read, at least to me. I will imagine, even if I can't prove that it's true, that the compiler could properly make the whole map static based on the use of the static keyword. How smart the compiler is, I don't really know. In my ideal world, those bytes are stored in memory exactly as a persistent state of the map would require, and then they are brought in directly as part of the BSS data segment, and pointers are established, and that's it. Now, I have serious doubts about it actually working that way, though. Now, if this is the code that constructs the map, and it has to be interpreted rather than simply built up from data in memory, it's hard to predict what the performance would actually be like. The reality is that this map is absolutely not in a performance pathway for us, so it ultimately doesn't matter in our case. When I was raving about how clear the C# code was to read, well, it turns out that the Java is just as clear. This version of runSiv, including the getBit and setBit functions, seem pretty clear. Perhaps it's worth noting that even the C standard library provides options for the data type in which you can store the siv bits, a bit set class and a vector of bools. When I was younger, man, a vector of bools just meant you were wasting a lot of bits, but now the standard library has a specialization for vector bool that uses a single bit per boolean, and it seems quite performant. So I was a bit surprised to find out that C++ was ahead of Java in that regard. But then when I looked into it further, however, I found out that Java does indeed have a bit set class, and probably has since Java 2, but it's just not being used by this solution. Well, that's curious. Did the author just not know about it? Well, digging a little deeper, the primesiv Java class, in there I found a comment that indicated that they eschewed the bitset class because it was slower than wasting a huge amount of memory by using an array of booleans. That means the sieve is using a full 8 or 16-bit word to track each bit in the sieve, and for those reasons, this solution is marked as an 8-bit solution to distinguish it from the ones that do it with a single bit. It'd be unfair to compare the two directly, so I try not to do so. Jumping on down to print results, we can see that it's very clear and easy to read as well. To write to the console, you call the printf function on the system.out object, which is an instance of a printstream object. The formatting largely follows the C language printf conventions. Now, before we can drag race C# and Java, we need to make sure that it's a level playing field. As noted, the Java version uses 8 bits per candidate integer, so to be fair, we should really compare it to a C# implementation that takes the same shortcut. And fortunately, the fancy multi-sieve implementation that we looked at earlier actually has a direct Boolean implementation so that we can compare apples to apples, and that's how we're going to race them. Both the C# and the Java versions will use a bool instead of a bit to keep track of the candidate primes. It's time to race them. Let's get them staged and launched and see what numbers come out the other end. If you're ready, here we go. C# versus Java. Wow, that's easily the closest race we've had, and I'm both surprised and impressed. Surprised in that they're so close because I would have expected Java to have significant disadvantage if it had to interpret and then execute all these bitwise operations, whereas the C# version should be compiled down to straight inline code. And yet, the impressive part is not only that the Java version is competitive, it's the winner. With a score of 2112 to 2046, the difference is only about 3%, but a win is a win, and this round goes to Java. Remember that we will determine the overall winners for the entire competition by running a benchmark pass at the end of the project, after we've reviewed all the languages. And we'll be looking at the single-bit faithful implementations for determining the winner. That means there's still ample time for you to get involved and improve your favorite language's implementation. If you think you can tweak the C# version to put it back in front of Java, then by all means head on over to GitHub, try your theory out, and if the numbers hold, check it in. For now, we'll leave this round with Java victorious over C# by the slightest of margins. I think the big takeaway from this round is that the performance of the two languages is certainly comparable and that both are quite quick, approaching the implementation performance of the raw C version and coming in at about 50% of the speed of the overall current champion. It's time to update the leaderboard, but the problem is we don't just have a single-bit version of Java to enter on a leaderboard because none of them use the bit set. I'd really like to have a faithful single-bit version of the Java prime sieve, so if you're a Java optimization wizard, by all means, get on it, would you? So now that I'm in the full swing of the languages series, I don't want to randomize the channel with videos of my daughter's baby chicks running down the hallway and stuff. So if this little weekly dose of Dave isn't enough, you can always find more on my other channel, Dave World, and by following me on Twitter at DavePL1968. I post a lot of stuff that I think is interesting but just doesn't merit an episode. You can find a link to Dave World by visiting the Channels tab of this channel. I've also been live streaming a little bit in the last few weeks, but on topics such as audio beat detection and RGB LEDs and so on, so stuff that isn't related directly to the language series at all, most of the time anyway. I did do one where I used the NSA's Ghidra tool to hack my way through the C-Lang and GCC versions of the C prime code, so if you're interested in the real deep nuts and bolts, check the channel homepage for a recording of that live stream. Otherwise, there are just 3 things that you need to remember for next time. Number 1, head to the video description for a link to that GitHub repo so that you can go in and check out the code on your own. Just look at it, improve it, whatever you love to do. Number 2, enlist in and improve any solutions in any language that you can. To me, improvement can be in any of the dimensions of performance, readability, compactness, or robustness without compromising it in any other dimension. And number 3, and I cannot overstate the importance of this, please make sure you're subscribed to this channel. Doesn't matter. You won't actually get notifications unless you turn on the bell icon or enable personal notifications anyway, but it makes me happy. And I gauge the success of an episode largely by how many new subscribers it garners, so if I'm going in the right direction with this one, or if you like that intro, let me know by subscribing.
Do it, Glenn. Do it. Do it.
We've got a solid 50 languages to choose from for the next episode, so if you've got a suggestion for which ones to feature in an episode, please let me know in the comments. I'm always curious how people would suggest that I group the languages for comparison, so if you have an idea, let me know in the comments. I actually do read and respond to them daily, or I try to, so it's my primary way of staying in touch with the viewers. So thanks for joining me out here in the shop today. In the meantime and in between time, hope to see you next time, right here in Dave's Garage. Remember that both are statically typed declarative languages that imitate the syntax of the C++ language to a great degree. To a great degree. Baby Stig here stayed safely in his box for more than 20 years until I came along and rescued him from the neglect. Remember, now, next we'll take a look at the other C# solutions. Wow, that's easily the closest race we've had, and I'm surprised. Speaking of English. For now, we leave this round with Java victorious over C# by the seashore. I think I said in there somewhere. I did do one where I used the NSA's Ghidra tool. Ghidra. Remember, it would add the top two values that it finds at the top of the stack, and then it would give you the